everything disabled. Okay, fine. And you can continue chat about anything because chat is not really recorded. So yeah, in this lecture, we'll dig really deep into multiple regression, which is really the most versatile and most important tool in quantitative research nowadays. What we learned before, such as analysis of variance, can be considered as a specific case of multiple regression. So we're going to really dig deep into this method, and if time allows, we'll go into research design. But after I've prepped for this lecture, realized they might not have any time for the research design part. The files that are for today's lecture, you can find it in the Dropbox. So it's this Excel file. Let me know if you have problems finding it, or if you go to I still haven't uploaded into Teams yet. So if you can find couldn't find the data, you just let me know. So there are also the two SPSS files from previous lecture. So make sure you have it open. Actually, you make sure you have it. You have it at the open and run the syntax before you start, so you can make sense of some of the outputs that I'm gonna show on the screen. So last lecture we mostly focused on the bivariate correlation and regression. I might have to ask you guys about the discussion about chipman into private if you prefer, because this is popping up and this kind of distracting. So in the bivariate situation, we're dealing with a single predictor and a single criterion, and you have you build a linear relationship model, and the model can take the form of raw score. If you have raw score, you will just use the raw score of x and y and with intercept a, and the standardized scored form, which you don't have an intercept. In the raw score format, the b, which is is called unstandardized regression coefficient of y regressed on x, and a is the intercept, and r, which is the regression coefficient in the standardized scored form, happens to be the Pearson's product moment correlation coefficients between x and y. So this is the case when there are only two variables involved. And in order to depict what is b and what is intercept and what is b can be also considered as the slope, which is the unit of changes in the dependent variable as the independent variable changes by 1 unit. And you can see on the graph, this is depicted on the regression line, whether the x changes by 1 unit and b changes and y changes by b. And the b0 here, sorry, I just copied some graph from the internet, so I didn't have time to change anything. So the b0 here is the a that in our slides. So that's the intercept, which means that it's the regression line that the intersection between the regression line and when the x value is 0 is on the y-axis. So which indicates when x is 0, the value of y. So this is another way of looking at the regression. And the error term is what we call the residual, which we're going to review in today's lecture as well. We talked about how these b and r are somewhat connected. So you can see that these are just the equations of the b and r. Okay, and the thing is that the r and b transformation in this case is quite straightforward. So R is just simply equal to B, but then scaled by times the standard deviation of the predictor divided by the standard deviation of the criterion. So it's like scaled by the two standard deviations. So it's B scaled according to these two standard deviations, which makes sense because R in this case is just a standardized form of B. Okay, so this is when there are only two variables, and R squared, which is basically R squared, indicated the percentage of variance in Y accounted for by the whole model. In this case, the whole model is just only one independent variable. So this is can also be understood as the accuracy of the model or the accuracy of X in predicting Y. And we can do some perform a very similar analysis of variance on the regression model, as you can see to the right. We can break down the variance in Y into the regression, the variance accounted for by the regression and residual. And this only not this equation to the right, and the way that the variance is broken down not only applies to a bivariate situation, it also applies to multiple regression. And the analysis variance can be used in the F-test to test. You can call it to test whether the regression model is significant or not. So whether the regression model can significantly predict the dependent variable. So it is an F-test. So if it's a single predictor, it's basically testing whether R is different from 0. Okay, so it's equivalent to a t-test of testing whether Rxy is different from 0. So this F-test. And in Excel, we kind of demonstrated that. So let me just show you the Excel file from the previous lecture. So in the bivariate correlation section, you can see that I've done a F-test and a t-test. So the F-test is a test of the entire regression coefficient regression model. So it's a test of the R square, and the t-test is just a test of whether R is different from 0. And you can see that these two, although the values are different, but they give you the same p-value. So which indicate that these two tests are very similar tests. Again, the t-test is just a test of whether the R is different from 0. The F-test is a test of R square, right? So that's that. That's a bivariate correlation and regression. But we're going to move on to multiple regression. So multiple regression in this case include more than one independent variables instead of just one independent variables. And it has multiple applications, such as establishing a prediction equation, right? You want to predict the values of Y, and you want to select a subset of predictors that are the best subset of predictors. And notice that the subset is important. Instead of selecting a single predictor versus another predictor, it's selecting a set of predictors. It can be used for analysis of variance. It also can be used for assessing a moderation or mediation. We haven't talked about mediation yet, but we're going to illustrate how this can be done to test moderation effects, like the way we did in the analysis of variance, where you tested the interaction between the two categorical independent variables. So there's an important point to make here, is that there's a common misunderstanding about using multiple regression or multiple correlation to identify good predictors. That's not the case. You cannot really identify one predictor against another. That to identify that, you can just simply use the correlation coefficient R. But it really, what multiple regression does is to identify how one predictor adds to the prediction when there's already another predictor in the model. So we're always talking about one predictor relative to the other, or Y controlling for the other predictor. We'll see that in an example. So the example that I'm showing here is really the example from the SPSS data that I was able to show you at the end of the last lecture, previous lecture, but we weren't able to go deep into it. So here we're going to look a bit more deeper into this. So if you haven't done it yet, please have the two data files open. So let me just quickly open the data file and run it so we could be on the same page. So we talked about, we illustrated how, just move this away. So this is the lecture 8 data file here. It has x1, x2, and x3. And if you want to do it, you can just simply run the syntax that was included in the syntax file, this regression syntax down here. If you just simply run it, you will be able to see all the results of that I'm about to show you. So here it shows the correlation between the three variables. So you can see that the zero order correlation, no, we'll just call it R, the zero order correlations. So basically it's the correlation without considering any other factors between the two variables. So you can see that we have employability rating, we have rating about the candidate's compatibility, how well do you think that he will fit in, and also competence, like how competent do you think the person is. So you can see that the three variables, and R12 is indicates the zero order correlation between x1 and x2, and R23 and so on. And you can see that they are highly correlated. Each of them are highly correlated with each other. So this is the zero order correlation that we are dealing with here. And so that's it in the SPSS. We can see the Pearson's correlation, and we can see the significant level. Okay, and so now the multiple regression basically in the raw score form, in this case, put both x2 and x3 into the regression into predicting x1. In the raw score form, it's indicated by B. So B is still unstandardized regression coefficients of xi regressed on xj. So 1, 2 is x1 regressed on x2. 1, 3, x1 regressed on x3. And in the standard score form now, we don't have R anymore, we have beta. So beta is standardized the regression coefficient in the multiple regression model. So remember, when there are only two variables, we have R, and here we have beta. Now, these regression coefficients indicate each independent variable's contribution relative to the other. So like y controlling, by relative to, I mean why the other factor has been controlled for. So add on to the prediction of the other variable. And the B and beta you can easily transform back and forth. And it's similar to how R can be transformed from B. So here beta is just is equal to the standardized regression. So it's the unstandardized regression coefficient times the standard deviation of the predictor Sj divided by Si. So for this purpose, I have included some basic calculations in the Excel spreadsheet called the lecture 8 and 9 multiple correlation. So here you can see that those are the three variables that are included in the SPSS file. And here are their zero order correlations using the Excel function correl. And here, there's the beta here, and we'll get into beta soon. But this is how B, okay, here I'm using B to calculate, beta to calculate B. So basically inverse of the equation that I'm showing in the slides. But here you can see that the B are estimated from beta, and the standard deviation of x1 and x2. Okay, so you can see that the color code of these in the formula indicates which values are used. So they use beta and these two. So if you look at these values of B and C intercept, you will notice that they are basically the same as SPSS. If you can bring them up, they're basically the same as SPSS results. If you want to check, they are the same. Okay, so I'm not going to check that one by one. So that's that. So this is the SPSS results, right? And this is the most important one that usually people look at. So the first half, you can see B and the standard error estimation of B. And in the middle, you have beta. They call standardized coefficients beta. And you can notice that in this case, there's no constant. So constant is the intercept. There's no constant because the intercept in this case is 0. And moving to the right, you can see the test of B. So unstandardized B's against 0. So the significance levels, which is what we know as, it's really the p-values. And there you have the 95% confidence interval for the B. So in this case, you can see the p-value for x2 is 0.031, is smaller than 0.05. While the p-value for x3 is 0.42, which is not significant. So this is a little bit different from what we saw earlier, because the zero-order correlation of the three variables are all significant and pretty high. But once you've included x2 and x3 both in the equation, in the regression model, the correlation for the coefficient for x3 becomes non-significant. So these two tests of significance of the B for x2 and B for x3 really indicates that which variable can add significantly to predicting x1 when controlling for the other variable. So a B for x2 is significant, which indicates that x2 adds significantly to predicting x1 when the x3 is in the model. On the other hand, for x3, it indicates that x3 does not add significantly to predicting x1 when x2 is in the model. Okay, this is all that is. And you can also make a note about these two significance levels, for x2 and x3, because we're going to come back to that and to see that what it actually means, or what it means from a different perspective. And what are the B's here, right? If you if you have one predictor, it's easy to understand what B is, what slope is, because you only have a two-dimensional graph. But for when you have two predictors, you need really not just a two-dimensional line graph, but you need a three-dimensional plate of it's like become a plate instead of a line. So the red lines draw a plate on the three-dimensional space of x1, x2, and x3. So the B2 and B3 are just the slopes of x1 on x2 and x1 x3 when you control the other variable. And here it also assumes that the two variables x2 and x3 are independent. It doesn't really consider the case whether they might be correlated somehow, which we know is not the case. But if you only include x2 and x3, they are treated them as if they are independent with each other. And there's the second thing that important statistics here is the multiple correlation R. So in this case, notice that I'm using the capital R instead of the small r as to differentiate between a multiple correlation and a zero-order correlation between two variables. So R could be best understood as the correlation of the obtained variables, which is the observed variables, okay, and the predicted values of the criterion, which is the dependent variable. And what do I mean by that? Let's just use the exercise 1 of the Excel spreadsheet to see what exactly I mean by this. So let's go to the Excel sheet, and I'm just going to maximize it. So on the Excel sheet, I have given you the regression equation here. So it's x1 equals c plus b2x2 plus b3x3, when I have already given you the values of b2, b3, and c. I would like you to do is to use these variables, use these three values, and x2 and x3 to calculate x1 for each x2 and x3 pair. So here's the predicted values, right? So I would like you to write a formula. So basically what equals, how do you say it? Like using the values of B, C, and B's to write the formula. So here, it's difficult for me to keep them both on the screen. And so I'm just going to use the SPSS values to results to do that, because SPSS also gave us the regression coefficient, right? So here's the SPSS regression coefficient. We know the C is minus 0.771, x2 and x3 are given. So with those values, we can write a formula to predict x1. You can use those three cases as well. So C is here, right? F29 plus, right? B2 is F27 times each x2 is, you click on this, plus F28 times x3. Now, the tricky thing is that if you use this formula, if I'm just using this formula on the screen, you know that if I'm just going to use the formula that I just written, let me just put it in again. Plus, that's B2, which is x2. You times that by x2 value, plus B3 is for x3. You time that by x3 value. Let's just click enter, and you have a predicted value. But the problem with that is that this formula, if you drag it, it's going to change from F29 to the next column if you drag it by column. So we're going to use the absolute reference, right? Remember to put a dollar sign before the F and 29 so that everything is fixed. And put a dollar sign between F and 27, so you want a fixed value. And C3, you don't really need it to be fixed, because we'll be just going to drag it downwards. So, and that doesn't need to be fixed. But F28 needs to be fixed as well, okay? So you're basically using this so-called absolute reference in order to prevent the formula from updating when we drag the formula. So now we can just drag it across rows first, or column, whatever you prefer. Across the rows, sorry. Then you get what's called predicted value. Okay, so with the predicted value, you can see that for each observation, there's a predicted value, there's an observed value, right? The observed value is what we observed earlier, and predicted value is just what we predicted from the equation using x2 and x3. Okay, you can now calculate what we call residuals, which is basically the observed values minus predicted value. So you can use the formula as well, right? So you use x1, right? Minus, that's x1 prime. So that's the residual. So there's nothing too complicated about residual. It's just the difference between the observed score of the dependent variable minus the predicted score. Okay. So now what I would like to test, so we have the residual. Step 2, we've calculated residual. Step 1, we've calculated predicted values. So is there any question about this? Okay, so I hope this is straightforward. the third case is that we want to calculate this multiple correlation called R1.23, which I use 1.23 to indicate x1 regressed on x2 and x3. So again, what we learned earlier is that this multiple correlation is just the correlation between the predicted value and the predicted value and the observed values. So it's basically a correlation between x1 and x1 prime. So to do that, we can just simply use the Correl function that we know. So we can enter equals Correl, and then we need two different arguments, right? So the first argument is the array 1, which is basically a selection from x1 to x12, x3 to 12. So we B3 to B12. Whoops, all right. B3 to B12 again. Yeah, okay, so that's the first argument. And then the second argument, we can just select the predicted value, right? That's predicted value. So we got the R equals 0.8820, okay? So if we compare this to what we had in the Excel, in the SPSS, we can see that in the SPSS, we also found that R is 0.882, so which is the same as we got from SPSS. Right. Smaller. So so that's just confirms the well, it kind of confirms that, you know, what R really is just a correlation between observed value for the dependent variable and the predicted value, which is the value that we got from the regression the regression equation. Okay, so that's the concept of this multiple correlation. And a multiple correlation, it also has this formula, which is the square root of beta 12 times R12 plus beta 13 times R13, which I actually I did it on the Excel. I have estimated R here. Here I have R here, and this is if you click on this, you will notice that this is the formula that I showed on the slides, which utilizes the beta here, the beta values, and R, right? So for that, we also get 0.8820, so which is the same value as we got from using the other method. So that's good. So which means that everything seems to be fit together. So that's that. Okay, so this estimating, you can also estimate R using beta and zero order correlations. So what this really shows, what the meaning of this is just that it's a multiple correlation of the dependent variable with the two independent variables as a set. Okay. And here is where you can find it in SPSS output. You have R and R square. And you also have an ANOVA, which is analysis of variance that analyzes tells you the significance of the entire equation, or the significance of the R square, you can say it. So this is the F-test. You can see that F-test is related to R square and the number of predictors and the sample size. So N is the sample size, P is the number of predictors. So the first degree of freedom is the number of predictors. The second degree of freedom, which is the error term, is decided by sample size and the number of predictors. And you have R square. So basically what the F-test does is to test the significance of R square, you can say that, okay? And I also did the F-test in the Excel data file. Here is the F-test using the formula that I just showed you. And this is the significance of the F-test using what we know about F distribution. So you can see the F value is 12.25. If you want to compare that to the, if you want to compare, you can compare that to what you got in the SPSS if you want. Let's just show that. See, so that's the results from SPSS to the left. You can see that F is 12.259, which is the same as the one in the Excel, and the p-value. Okay, so that's the F-test. And what it does is to tell you whether the whole regression model is significant or not. You can think of it that way. There's also a case of, so R square, another way of understanding R square is it indicates that the percent of variance in the dependent variable that has been accounted for by the entire regression model. Okay, and one interesting thing in it is that we can use the change of this R square to indicate when a new predictor is added to indicate how much the new dependent variable adds to the prediction. So to illustrate that, I've included some tests in the spreadsheet as well, and which I will first show you how to do it in the spreadsheet, and then we can move on to SPSS. So you can see that there's observe of change of R squared from 1 to 2 predictors. And R squared for model 2 is just the square of the zero order correlation between 1 and 2. So that's simple, right? So you have the zero order correlation here between R1, 2, and R squared when you have only X2 as the only predictor is basically the R, the zero order correlation squared. The same for R squared 1, 3 for the model 3. So that's our R squared for the model 1. And we can calculate the R squared difference by subtracting the R squares across models. So we can, the R squared difference cost, or the change of R squared, by adding the X3 to model 2, which produces model 1, is the 0.78 minus 0.75, which is only 0.03. So you can see that adding the X3 only increased the prediction, only accounted for an additional 3% of the variance in addition to X2. Okay, so remember R squared is considered the percentage of a variance accounted for by predictors, right? And so you can see that X2 by itself already accounted for 75%. So adding X3 doesn't really add that much, but a model with X3 only, it only accounts for about 55%. If you add X2, you can calculate the R squared difference between model 1 and model 3, which is 0.23. So that's so adding X2 to X3 leads to an additional 23% of variance in X1 being explained. Okay, so it seems like adding X2 to X3 adds more as compared to adding X3 to X2, right? And also in this case, you can see that the model 2 and model 3 are both called nested in model 1 because model 1 has 2 variables and model 2 and 3 each has 1 variables. So the model 2 and model 3 are kind of included in model 1, or nested, not included. So this is what so-called nested models. We can test the R squared differences, right? So we can further test the change of R squared, the significance of the change of R squared when you add variables to an existing regression equation by using this F-test. So you can see that in its essence, it basically tests the difference between the significance of the R squared 2 minus R squared 1. So it's an F-test that does just that. And we have done this. We have done this in the Excel using the formula that are displayed on the screen in the PowerPoint slides. So you can see that for model 1 and model 2, we did the F-test to the, and you can see that the F-test is significant, which means that X2 adds significantly to model 3. And you can see that for the model, the difference between model 1 and model 3 in terms of R squared is not significant, which means when we add X3, we didn't really add significantly to the prediction model. And if you, interestingly, I made the point here, if you compare these two p-values with the p-values from t-test of the unstandardized correlation coefficient, which I'm about to show on the screen here. So those are the p-values for x2 and x3. And you can see, and these are the p-values for the t-test again, right? Just to remind you, the significance value I'm showing in the PowerPoint slides are the p-values for the testing each unstandardized regression coefficient b against the 0. But you can see that for x2, the p-value for that for x2 is 0.031, which is the same as you get from the p-value testing adding x2 into x3 into the prediction of x1 on top of x3. The same applies to the p-value for testing the b of x3 is the same as testing the p-value for R squared change. Okay, so that's just one thing that to keep in mind. So which means that the interpretation of the t-value of the p-values for these testing of the unstandardized regression coefficients is quite similar to, they can be interpreted in the same way. That is how much this one independent variable adds to prediction on top of the other independent variable, okay? So that's that. And you can also, if the R square differences of R square I'm showing you on the Excel file is a little bit too much for you, you can also do it in SPSS. So which I'm about to show you how to do it in SPSS. So here's the SPSS file. I'm bringing it to the right. You will be, so we have, again, we have x1, x2, and x3 on the screen. So you will be using the analyze again, regression, linear, and then you can put x1 as the dependent variable, but for independent variable, you can add differently, right? You can add different blocks. So you can see that there's a little thing called block 1 of 1, and you can add more blocks into it. So for the first block, let's add x3 into the independence, and the method, let's keep it enter, okay? But instead of going to, you can click next. You can click next, and then it will ask you to create a new block. So for this block, let's do another model. Now this time with both x3 and x2 in the model. Again, the method is enter. So now we have created 2 blocks, okay? So the first block indicates one regression model with only x3. The second indicates another different regression model with x2 added into the previous model. So these are 2 nested models, right? So the first model is nested in the second model because it adds the second model has an additional independent variable. Now before we move on, we need to go to statistics, okay? And here's a bunch of statistics that you can include. But the most important one is called R squared change because we want to see the R squared change. Okay? And you don't have to, this, like if you don't want it, you don't have to click on the other ones. But let's just include R squared change and continue. And without doing anything else, you can paste it and then run it if you want to keep it. You can just paste it. Where is my, let me pull out my syntax. So this is what it has as shown up in the syntax. You can see on the syntax, it has method enter x3 and another method. So there are 2 different methods. Let's just run this. And you get a new result here, okay? And in the new results, which I also included in the PowerPoint, okay, so basically you create 2 blocks and make sure you have clicked the R squared change. And then the results will now include change statistics. So model one is basically f change is basically from nothing to something, right? So the model one, you can ignore it because you can see that model one only has as you can see from the notes, model one, you only have predictors x3 as the only predictor. And so the change, f change for model one is really change from 0. And you can see for model two, there's the R value and there's the change of f value. Now that you can see that the significance of f change, right? So the R square change is 0.228, and that's the test. The f test tests the significance of this change, of this R square change to the left, 0.228. Now you can notice that this is also the same as the result is also the same as what we get here. So here's the Excel results that uses the equation that I wrote, that I presented in the slides, to do the f change, f square change, f test for the R square change. You can see that the values from model 1 to model 2, which is what we tested here, is 7.19. You got 7.19 here. The p-value is 0.03. So here we didn't really test the difference between model 1 and model 3. And if we do that, we will get the same results as we got here, as we got in Excel between model 1 and model 3. So in order to test the model 1 and model 3, you will have to include x2 in the model that you were comparing to instead of x3. So instead of x3 here, if you enter x2, you will be comparing two different models. So you can do that on your own time. And you can also, again, the change of these, the change in terms in R square, the test of the change of R square produces the same p-value as the test of B against 0. Okay? The last bit before we go and take a break is the so-called partial and part correlations. And if you look at the results that from SPSS output, you can see that we've also included, if you ask for it, we will give you the partial correlations. Okay, so the first is zero order correlations, which we already know what they are. It's just a correlation without considering any other variables. But now you can see that there is partial correlation and part correlation. So the partial correlation, and both are indicating the correlation with x1. You can see that for both x2 and x3, the partial correlation with x1 is smaller in terms of value than their zero order correlation. But it seems that for x2, the jump, the decrease from zero order to partial correlation is lower, it's smaller compared to x3, where the correlation went from 0.74 to 0.30, which means that in the partial correlation, something happened, and we know that something is because now you've started to control x2. But there's also part correlation, right? Part correlation is even smaller than partial correlation. So what is partial and part correlation? So here is the equation and the concept. So we write partial correlation as R12.3, okay? And what it means is that's the correlation between x2 and x1, but after the linear effect of the other independent variable, which is x3 in this case, have been removed from both x2 and x1. Okay, so you're basically controlling for the correlation between x2 and x3 and the correlation between x1 and x3. So the influence of x3 on both x2 and x1 has been removed. Okay, so the equation is down there in the case you're interested in. You can see that on the denominator, it's R12 minus R13 and R23. So it means that subtracting the product of R13 and R23 from R12. And on the denominator, you can see that it's the error term, the standard error of the standardized, how do I say, the standard error term for the for R And you can see it did for both R13 and R23. And part correlation is also called semi-partial correlation, is written differently as R1 parenthesis 2.3. This indicates that it is the correlation between x1 and x2, but you've only controlled for removed the linear effect of x3 on x2. So in this case, the linear effect of x3 on x1 has not been removed. Now you can see the equation is very similar on the top, but on the denominator, you only have the R23 as the denominator. Okay, so you don't have the R13 in the denominator. So that's the form of equation here. And you don't have to really remember these equations, but in terms of in the concept, it might be easier. The conceptual definition might be easier to remember. So what it really, another way of looking at it is just it depicts the effect of x2 on x1 when x3 has been accounted for. Okay, so what x3 has been added onto the prediction. So how x2 adds to the prediction of x1 on top of x3. So. And in Excel, I have calculated this based on these equations. You can see that I have the partial correlation calculated here using these equations of R12, R13, and R23, and N. If you want, you can examine those equations or write your own ones if you're interested in. But that's that, right? And if there is any transformation going on between any of these correlations and beta, is that the part correlation and the beta, okay, are kind of, you can transform back and forth between part correlation and beta. Notice that it's not partial correlation, but part correlation or semi-partial correlation. And so beta 2 is basically part correlation between 1 and 2 controlled for 3, divided by the standard error term for correlation between 2 and 3, x2 and x3. And beta 3 is the same. So they're scaled part correlations, you can say it, right? Scaled against the error of 2 and 3, okay, x2 and x3. And these equations are used to calculate the beta here in the Excel form. And that's how I calculated the beta 2 and beta 3. And if you're interested, you could look at the equation and calculate it yourself. So that's beta, okay? And if you compare these to the SPSS output, they are the same. So let's take a break for now, and when we come back, we'll look at further at the assumptions of multiple regression that we didn't really get to look at. And so we have a break. Now I'll put the Mentimeter link, Mentimeter on the screen. And when we come back here, we're back in 5 after 2. Pausing the recording. Okay, welcome back. So I've presented quite a lot of stuff. I don't want to make it too complicated. For most of the time, when you use multiple regression, you would only be caring about only a few statistics. Most people will just care about the B and sometimes the beta, whether the B unstandardized coefficients B's are significant or not, and also the whether the entire equation, the regression model itself is whether how much variance in the dependent variable does it account for, R and R squares. So most of the time, you just, when you report the results, that's what you will be reporting on. And when you test these R-squared changes is just a test of comparing different models. But what I'm showing you, like partial part correlation, is just another way of illustrating what exactly they are, right? What these values actually are, and what these tests actually do. And for R presented here, we know that this is simply the correlation between the predicted variable, the predicted values, and the observed values for the dependent variable. Right? So those are just some of the, I would say, like these background knowledge. I think it's good to have when you use the regression for the analysis, you know what it is doing. So further forward, we didn't really address the assumptions behind multiple regression analysis. We know that there are 3 parametric assumptions in general for parametric tests, and multiple regression is definitely a parametric test. The unstandardized regression coefficients B's are an estimate of a parameter in the population. That's why it comes with standard error. And remember the parametric assumptions are independent samples, normal distribution. Can't remember the other one. What is the other one? Independent samples, normal distribution. What is the third parametric? Anyway, check the lecture. That I should know that, but yeah, it should be like this right there. Normal distribution. Anyway, for multiple regression, you need some additional assumptions. First of all, it has to be a linear relationship between the IV and the DV. We've shown that if it's not a linear relationship, then we'll fit a curvilinear model instead of a linear model. So this can be easily done by check the scatter plot, where you plot the x against the y, independent variable against the dependent variable. Gets a little bit more tricky when there are more than one independent variables, but you can have scatter plot for each independent variable. You don't have to use a 3-dimensional scatter plot or something like that. The second is that the residual should be normally distributed. So this is a little bit different from normal parametric assumption that assume normal distribution of the independent variables, which is also important here. But the residuals, remember, residual is just the difference between the predicted value and the observed value. The residual should be normally distributed, which means that we should check the distribution of the residuals using residual plots. In fact, residual plots is something that's really important for any kind of linear models that you should always check and know how to read. The third is the lack of a multicollinearity. That is the independent variables that you've included, they're not highly correlated with each other. So there's something called the variance inflation factor, that goes VIF, that can be used as a rule of thumb to check this. And the last one is again, try to read it again, homoscedasticity, which means that the residuals should be similar, evenly distributed across all the values of the dependent variable. Did I say the independent variable? It should be the dependent variable. Should be the dependent variable. Okay, somebody pointed out. Homogeneity of variance, yeah, across different, that's for ANOVA, yeah, across different groups. So this is actually, okay, so these assumptions are some kind of a specific form of these 3 assumptions that we mentioned earlier. So it's not in addition to them, but it was like they take a different form. So homoscedasticity is really about the homogeneity of variance, but across all the values of the dependent variable. So for this, we can check the plot of standardized residuals versus standardized predicted values of the dependent variable. So let's go to see specifically how we can test these assumptions and what to do when some of the assumptions are violated. The residuals, again, is just the difference between the observed values and predicted value. And here it is. You can see the spreadsheet with the exercise we did earlier illustrated that. And to depict that, you can just see that. So those dots are the observed values, and their values on the y-axis is just the observed values of the dependent variable. And you can see that you have a regression line, which indicates your predicted values of y when you project each dot on the regression line onto the y-axis. And the residuals, you can see you draw a vertical line, which means that it's the difference between the observed values of each y and the regression line, so the distance between that. And the so-called ordinary least square is basically fitting a regression line that minimizes the sum of distances squared between the observed values and the regression line. So in order to track the distribution of the residuals, you need to use the so-called plots to draw certain plots. So to check the distribution of residuals, you have to click the histogram and normal probability plot. And this I have already done that for you in the syntax. So this has already been done in the syntax. All you have to do is just run the syntax, you will get these histogram and normal probability plot. And here are the two plots. The histogram itself is just the histogram of the standardized residual on the on just basically a histogram for the residual. And in our case, we have only have how many? We have 10 observations or less than that. Yeah, 10 observations. So it doesn't really tell us much. But ideally, the standardized residual should actually be normally distributed. Okay, at least it should be more symmetrically distributed. It is only when it's not symmetrical does it really show some problem. The PP plot is another form of plot to check the normal, whether it's normally distributed. So those dots are just dots that project the observed standardized residual into a probability normal distribution, probability indicating normal distribution. So it's just another way of looking at whether these residuals are normally distributed. So you want those dots to be close to the diagonal line. So the more close they are to the diagonal line, the closer it is to normality. So if they are deviated from the diagonal line, there's some kind of deviation from normality. Again, these are just eyeballing methods with no tests of whether this is different from normality or not. So if you really want to test, you provide a test, you can use the Wilkes-Shapiro test. Is it Shapiro-Wilkes test? You can calculate standardized residuals in SPSS and then test that against the again using the Shapiro-Wilkes. Is that Shapiro-Wilkes test? To test whether it's actually like provides you with some kind of a p-value, whether it's significantly deviated from normality or not. So that's that. The second is multicollinearity. We have, if you look at the results on the standard where they on the table of the regression coefficients, if you ask for the VIF multicollinearity data, you'll notice that towards the right end of the form, it gives you the VIF for each predictor. So this is the case. You have two predictors. You can see that although these two predictors are actually highly correlated, the VIF doesn't really suggest so. If the VIF is smaller than 10, or in some cases smaller than 5, it's fine. That's used as a rule of thumb. And what VIF really does is how much larger the standard error for an independent variable increases compared to if it has zero correlation to other independent variables in the model. Okay, so how much the correlation inflated the standard error. If its standard error is inflated, then it's less likely for the regression coefficient to become significant because it's divided. So because the t-test is basically dividing the b, okay, by the standard error. So if the standard error is inflated, then you're less likely to get a significant result. So which means that your p-value is kind of what's called, how do you call it, inflated. It's larger than it actually what it actually should be. Okay. So homostasticity is a little bit more tricky. So we showed earlier that this can be done by plotting the standardized predicted value, which is z-pred in this graph, put it on the x-axis, and create a scatter plot of the standardized residuals on the y-axis, which is z-resid. Okay, z residual. Z means it has been standardized. You don't have to do anything to get those. Those values are already automatically included when you click plot in SPSS. So to the right, you have the scatter plot for our variables, which again, you couldn't really tell. What we are looking at is whether this the standardized residual is evenly distributed across the standardized predicted value. So for this one, it's not that easy to tell. But what we are looking for is homostasticity. As you can see on the graph to the right, that's the same kind of graph: standardized residual versus predicted value, or standardized or unstandardized. And you can see that what you're looking at is that it should be symmetrically distributed from lower value to the higher value of the predicted variable. And it should be clustered around the lower single digit of the y-axis, such as 0.5, 1.5, or 4, not like 30 or 150, not too high. So, and it shouldn't have any clear patterns, that it should just be like some kind of, evenly distributed, like round shaped, or you shouldn't see any linear or kind of patterns, or especially curvilinear patterns, or patterns that goes from smaller to larger. So again, this is just an eyeballing technique to look at residual plots. And so here's an example, some examples of showing heterostasticity. As you can see, in both cases, the variance of the residuals, which is indicated by the spread of the residuals, seems to be getting larger as the predicted value gets bigger. What this means is that the prediction becomes less reliable. If you have a larger residual, which means that your prediction is more off, or at least the variance of your prediction start to become higher, right? So what these two tables shows is that there's some kind of pattern that as the predicted value gets larger, the spread of the standardized residual gets larger as well. Okay, this is a case where the residual is not evenly distributed along the predicted value. So this can be caused by a couple of reasons. So the example that they gave on Qualtrics is that, for example, in winter time, you imagine you're selling ice creams and you're recording your ice cream sale on each day, and you found out on the winter time there's not much variation. Basically, you sell very little. But on summertime, the variation that you got from day to day is huge, because on weekend people came out. So on weekend you got an extreme large amount of sale. So if you include the whole year stats, it's going to look like that, right? Which means that on the one end, for some predicted values, when the sale is higher, the variation is also higher, for example, right? So that means that what you should really do in the model is that you include season as a predictor. So there's some kind of moderating variable that's missing here, including the moderating variable such as season will help you to improve your prediction model. So this is the case that they gave in Qualtrics. In this case, like what happens and what to do, right? And what really means that the model can probably be improved by somehow, and it can actually inflate the p-value, which gives you a larger p-value that it should give. So which means less likely to become significant if the n is if your sample size is small. But in this case, they also pointed out the regression coefficients in the previous two cases might still be accurate. The solution is that you can either transform a variable by applying a log formula, a log function on the variable, so it becomes more evenly, so it becomes less more evenly distributed. And or you can also try to locate the missing variable. So a lot of these cases are caused by a missing variable in the model, such as moderators. So if you take account into those variables and find these variables, such as I said, you should take into account when you want to predict ice cream sale, you should clearly take into account not just day, but also the season, right, for example. So that's that. And there are other some unhealthy residual plots that you can see on here to the right. Other than the case when it's not evenly distributed vertically, you sometimes have outliers, right? Sometimes it's clustered to a specific spot, but then you have an outlier. And then sometimes you have a clear shape and pattern that's like U-shaped pattern. So if you have some kind of U-shaped pattern, you should either fit a curved linear model, or you can include a moderator saying that when the predicted value is small, there might be another moderator here, such as season or some variable that you haven't considered. So basically, this shows is that the linear relationship changes according to the value of the predictor on the U-shaped formula U-shaped pattern. And basically, it shows that you should consider including other variables in to see whether this whole prediction model can be improved or not. So they actually, on Qualtrics, which is the survey platform that a lot of researchers use for their studies, they actually give you a very good article about how do you interpret different residual plots, under what condition can each of these examples happen, and what to do about them. So I highly recommend that you check out this link. All right, so the next step, as I said earlier, the multiple regression can be used for different purposes. And one of the important applications is to engage in the moderation analysis. And again, the moderator is just when a variable that affects the directional strength of the relation between another IV and a DV. And to test for moderation is basically a test for interactions and how they interact with another independent variable to affect a dependent variable. We have shown in the analysis of variable example, how would you do an interaction when both independent variables are categorical variables, okay? But we didn't really address what happens when both independent variables are quantitative variables. So in the next part, I'm going to show you how this can be done using multiple regression to test do a moderation analysis of both quantitative variables, both independent variable and a moderator variable, which is just not an independent variable. Both of them are quantitative variables. In essence, okay, this is the basics. If you have three variables, again, I'm using three variables as an example here. If you have three variables, x1 predicted by x2 and x3, then what we need to do is to compute a fourth variable, x2 times x3, as the product of x2 and x3. So this product term indicates basically the interaction between x2 and x3. This product term is simply by like practically speaking, you just multiply each paired values of x2 and x3. Okay, that gives you the product. And then we'll compute two multiple regressions, first with the interaction in the model, and then without interaction term in the model. So now you have two R squares. One is R squared with one regressed on three variables here, 2, 3, and the product between 2 and 3. Okay? And then you have a regression model without interaction. So you only have one regressed on 2 and 3, but not without a product term. So you have two predictors. In the one with interaction, you have three predictors. Okay? Then you can just basically look at whether the R square change by adding that interaction term to the model is significant. Okay. Remember earlier we talked about test of change of R square across two nested models, and in this case we're just basically testing whether adding the interaction between 2 and 3 can actually improve our prediction. If this R square change is significant, then the interaction term is a significant predictor when you control for x2 and x3. So then you can say that either x3 moderates the relation between x1 and x2, or x2 moderates the relation between x1 and x3. And that's just a matter of a theoretical plausibility or interpretive easiness, which one is easier to understand. Okay? So the moderation can go either way. Which way are you interested in? It depends on your theoretical, depends on the theory that you're testing. And if you remember, the R square change is basically a t-test of the B associated with x2 and x3. So you don't really need to produce two different models in order to do what I'm describing here. You can only just look at one single model with the interaction term and look at the significant test of the regression coefficient for the interaction term. So here is the regression equation that for this model, right? Remember, notice that I've now changed the notation of b's a little bit differently. So instead of a and b, I'm just going to use all b's. So x1 prime equals b1, which is the intercept, plus b2 x2. So b2 is in this equation is the coefficient for x2, b3 x3 plus b2 times 3. So those 2 times 3 means that the interaction between 2 and 3. So if the test of b2, if the b2 times 2x3 or 2 times 3 is significant, then there's significant moderating effect, and we can say there's moderation. Again, this is a test of the b2 times 3 against 0. It's very important to note that I'm just going to pin my own video because I realized that give me a second. Okay, so but it is not necessary, this is important. When you're having product term x2, x3 included in the prediction model, you don't really care, you don't really look at other coefficients b2 and b3 in this particular model. So it's not necessary for any of the other coefficients to be significant. Once there is interaction, two-way interaction, you don't really care about the significance of b2 and b3. You'll still include them when you calculate what we call simple slope, which we're going to talk about later. The equation as a whole is still important. You just don't really care about significance of b2 and b3 anymore. So in fact, if there is a product term here, if you include a product term between x2 and x3 in the prediction model, then the regression coefficients of each of the non-product terms, x2 and b2 and b3 in this case, they have no interpretive value. Okay, you don't really interpret each one of them. So let's do a demonstration through an exercise. Let's hope to finish the exercise in about 20 minutes before we move on to the simple slope test. But let's go to the Excel spreadsheet that I've showed you earlier. Just put the SPSS away. Okay, Excel. So for this one, we're going to lecture 9, multiple regression with interaction. You notice that here we have 3 variables, x1, x2, and x3. So we want to explore the interaction between the 2 quantitative independent variables. Again, if you want to remind yourself, these are from different participants. You can create a participant variable completely to indicate that these are from different participants. So here's the mean for dependent variable x2 and x3. And you also have a standard deviation observed for each variable. Now I've copied the x1 into here, but here I wanted you to produce a variable called centered score for x2. Remember centering scores? Centering score is just minus each individual value observed scores by their group, by the mean. So centering the scores will make it easier for us for the next step to make the scores to make the values easier to interpret, especially value for the simple slopes. Okay, that's why we're centering the scores here. Another quite common thing that people do is people will sometimes standardize the scores. And here we're just centering the scores. And so we want to preserve the original scale of the 2 independent variables. We don't want to standardize them to a mean of 0 and standard deviation of 1. Instead, we just want to center them so they have a mean of 0. And remember, in the earlier lectures, we've shown you how centering the score can change the intercept. So making the intercept easier to interpret. And in this case, we're just trying to make the next step, which is test of simple slopes that you can see in the next spreadsheet easier. So to do that, again, to do that is quite easy. You just have to write equations that equals, x2, the value itself, minus the mean for the x2, which is the mean value here. So now you've entered basically you're entering 2 cells here, cell reference here. One is the original score, the C31 indicates the mean. Now again, we don't want to C31 to update once you drag it down or drag it across the columns or rows. So we're going to use absolute references for that, right? And if you are really lazy, you don't have to reference the column because you want to drag, when you drag across to the x3, you want it to be automatically updated to the mean for x3, which we know that locates 1 column over. So if you drag and update the column, it will be perfect, right? So let's not put a $sign in front of the C. Just put a $sign before 31. So when you drag it across the rows, the 31 will stay the same, and the C6 will update. Okay. So that's our equation here. Now, if you just drag it down low, it will automatically update. So now you can see now it's C7 minus C31, which is exactly what we wanted. So let's just drag it all the way, and we will have that centered value for x2, we call it center x2. C stands for centered. And again, because of annoying roundup issues, we ended up, instead of a 0, we got an extremely close to 0 number, but not exactly zeros, that we can live with. And for Cx3, we can drag it over and it produces a new formula automatically updated. You can see that because we did not fix the C updates to D when you drag across one column over, which is exactly what we want, D31. Okay? So now we have D6, which is this, because it automatically updated when we drag it to create a new formula over a new column. And then we can just drag it down. And then we have the centered values for X3. Now that has a mean of 0. And it has the same standard deviation as the raw or the original scores. The centering only changes its mean to 0. Okay? So that's what happened. So that's centered. And now we want to calculate the product term. Again, the product term is just the two centered scored. Okay, notice that if you use the centered scored for these two independent variables, you also want to use the centered scores for the product term. So you'll be calculating the product term for these two centered, using the two centered scores. So this centered score 1 times centered score for X3, you got 16.016. If you drag it down, it will automatically update all the formula. So now you have the variables. The other reason that I'm doing centered instead of standardized is because it's easier to center it in the Excel. In the SPSS, they have option of standardizing it, but they don't have option of centering it. So that's quite annoying, right? So we're centering it in Excel here. But if you are interested, I can show you how do you standardize it in the SPSS. So next step is to create a new SPSS data file. So we have the SPSS open. SPSS. So I'm gonna close the old data files and gonna create a new one. So this is the one that I created. So basically, I just copy and pasted the one from Excel here to here. So you basically select all the values and copy them, and then click on the first one. You right click. If you can't copy, Control V, right click and say paste, and it will all be there. And the variables that you created wouldn't name that, so you just call it CX1, CX2, CX3, CX2, X3 to know, so you can know what they are for. Okay. Now you might be so basically you will be building a regression model using these three variables as the independent variables and X1 as the dependent variable. So that can easily, so again, right? So these are the variables that we have. Again, you have to use the two centered scores to create the product term. And then basically you can just create this multiple regression model using all three variables and X1. And you can include, okay, so make in the statistics dialog, make sure you get a very important statistics that is covariance matrix, okay? So that's something that we hadn't asked for before, but here it's very important to have covariant matrix. You can also look at the collinearity diagnostics, but there's no need for R-squared change because we are just using a single model here. If you want, you can create two blocks, one with the interaction term and one without interaction term to make it more interesting, which is what I'm going to do here. Is that I will demonstrate to you to create two blocks, so to compare the two models. So you regression linear. So on block 1 of 1, you have two variables, but without their interactions. So you can click next, and you have all three of them. So include not just the two variables themselves, but also the interaction term. So it's very important to include the product, the variables without interactions in the model. Okay, don't just include a single variable indicating their interaction. If you include an interaction term, you always include the terms that forms the interaction, that is x2 and x3 here. Okay, otherwise the results becomes uninterpretable. So we now have two blocks. In the statistics, I'll ask for R-squared change, collinearity diagnostics, again, covariance matrix, and I will paste it, and then I will run it. And where did it go? Like it went somewhere here, okay? So and now you can see that these are the models that I have created. So the first one is without the interaction term. The second one is with the interaction term. So if you run this model, so this is the model that we've run. You can see that gives you the correlation term between the four variables involved. Two models. Okay. You can see that when you've included, when you have added the interaction between x2 and x3 on top of the model without the interaction, you can see there's a significant f-value change by adding the interaction. Okay, so the test is significant at the 0.001 level, and that's the value of f change. And as we have learned earlier, this means that adding the new predictor, in this case, the new predictor represents the interaction, right? We manually created this predictor, and we know what it means is the interaction. And adding this new predictor leads to a significant increase of the prediction of x1. The first block is just x2 and x3 without interaction term. The second block is with the interaction terms, all three variables, right? So these are the shown on the screen. You can see A's predictor is x3, x2, B predictor is x3, x2, and x3, x2. So there's interaction. So there's the ANOVA of the R square. And most importantly is you can see in the coefficient that in the second model, the p-value for the t-test of the unstandardized coefficient B for x2, x3 interaction is significant as it's smaller than 0.05. Okay, so if that's the case, here I'm just showing you the single model results. If that's the case, you can say that there's a moderation effect of either x2 on x3 or x3 on x2, depending on your direction of interpretation. Okay? Is that clear, or is there any questions about this? I'll let you run it a little bit. I'm gonna quickly pause the recording, and if you have any questions, you can let me know. Okay. So again, as I said, another way of doing this is to standardize the two predictors. You don't have to do anything about the dependent variable. First of all, you never do anything about a dependent variable; just leave it be. But you can standardize the independent variables. Okay. So the independent variable, if you want to standardize it, you can go to SPSS, bring the data out, untitled data. Okay, so we know that x2 and x3 has been centered. So in this case, I'm going to delete the third variable because I don't want to create any confusion about it. Okay, so there's no product term. There's centered. X1 is actually not centered. I don't know why I call it CX1. Just X1. CX2 and CX3, we know that they have been centered but haven't been standardized. So to standardize it, you can go to again, it's a weird spot to save standardized variable, but it's actually in descriptive, the statistics and descriptives. Okay? And if you click that, you can have descriptive statistics, but there's an option called save standardized values as variables. So you click that, and if you then click OK, not only provides you with descriptive statistics for the two variables, but it'll also give you standardized values of these two variables. So you click OK, and then it gives you the descriptive statistics, which we know that mean is 0, standard deviation is 3.04, 1.52, which we know. But if you go back to the data file, now you see that there are now two new variables called ZCX2 and ZCX3. They're just really standardized. You can see that the label is actually Z-score CX2, Z-score CX3. So now you have two standardized variables. And that makes it a bit easier to, if you don't really care about the scale of the dependent variable and the scale of the independent variable, right? So you better just scale it to a mean of 0 and standard deviation of 1. It makes it a bit easier for the next step. Now, next step is to compute the product term with the two standardized scores. And in SPSS, the computation is not as straightforward as in Excel, where you can just write a format in the cell. In SPSS, you have to go through some kind of another menu here. You need to use the menu in transform. Okay. Now in transform, there's something called compute variable. And if you click on that, it gives you a compute variable dialog. Right? So you write your target variable names in the target variable section. You can call this Z, X1, X2, because it doesn't matter if it's centered or not. The Z score and the Z center score is the same. So, and then you have to create a numeric expression to the right. You can send the variable into the numeric expression using the send button, and then you use times ZCX3. And then at this step, and there are many other options like using if and using different kind of functions. But let's just keep it simple, just the product term of Z score 1 for X2 and Z score for X3. So now it's you can either paste it or you can just select OK. If you paste it, you can see how the computation syntax is. It is something like this: compute equals. So that's the computation syntax. If you want to see it more clearly, I'm going to put it up. That's the computation syntax. So basically, compute Z equals the two Z scores. So I'm just going to delete these two centered scores. I don't want to cause any confusion. I'm just going to call it ZX2 and ZX3 instead of a CX2 because it's completely redundant, just for the sake of clarity. And we go to the SPS. We also call it ZX1, X2. Now, because we've changed the names, we also changed the name here. Okay, if you execute it, it gives you the product term in SPSS. So now you have the product term for the two standardized scores. So now you can do a regression using standardized scores, and you can compare the results to the unstandardized scores, right? So reset, and you have the standardized scores in, and then the product term of the two standardized scores in, and statistics, covariance matrix, or whatever. Let's just do it the simplest way. So now you have the standardized terms, standardized scores. You can see that the results are slightly different from what we got before. So the results are slightly different from earlier, but the intercept is the same. So to the right is using standardized scores. To the left in PowerPoint, this results from centered scores. And you can see that it changes the standard unstandardized coefficient B, standardizing the scores, but it does not change the standardized coefficients beta, okay? So the beta are the same whether you standardize the score or not. The intercept hasn't changed because we were using centered score before, which has a mean of 0. And we know that intercept means that the value of the dependent variable when x is at 0, in this case 0 is the mean score, but that hasn't changed because we were using, yeah, that hasn't changed, but that has changed the unstandardized coefficients, B, okay? It has changed standard error, but it hasn't changed the t-value and the significance values. So the test of these unstandardized coefficients B gives you the same results, okay? But this just shows you how standardizing the variable, what does it change and what it doesn't change. It doesn't change the beta, and it doesn't change the t-test results. T-test results. It does change the unstandardized coefficients B's. The value of the B's will change when you standardize the scores. So that's it for now. Let's give it a 10 minutes break. We'll come back at 3:05. And then as we come back, we'll take a look at how do we further explore this interaction. Okay? And the recording is now paused. So if we have a significant interaction, we need to explore it a bit further. So this can be done by reducing the two predictors, quantitative predictors, into a two-way table, and by solving this regression equation for high and low values of these two predictors. And what we usually use for high and two values, you just use 1, +1, and -1 standard deviation among the mean value. Now, since we have centered both x2 and x3, we're just going to do +1 and -1 standard deviation, okay, because mean is now 0. And this can help us to simplify the two-way interaction into a two-way table. But that can be done at the same time with the process, with analysis called test of simple slopes. And what it does is that it can create the slope of slope of the dependent variable against one of the independent variables, okay, for given values of the other independent variable, which is usually the moderator. So we can, for example, we can test the slope of x1 against x2 at two different values of x3. Okay, so we can have produces bx12, which x1 predicted by 2, but we can have two slopes, two b's, one at high values of x3, the other as low values of x3. Okay, and then we can test the significance of those two b's at each, again, we can test the significance of each of those two b's, okay? And this can also be, this can be done in the spreadsheet that I included earlier, which I'm putting on the screen right now. The final spreadsheet called test of simple slopes. This is the test of simple slopes here. And that's from another person, I think Jeremy Dawson, co.uk. So he provided this spreadsheet on his website. And if you want, you can still download the spreadsheet from his website. It's there are other spreadsheet there as well. And as you can see that in this case, he was having in this case that he was included as an example in his original spreadsheet. You can see that he was using a gender as a moderator to test the difference between an independent variable and a dependent variable, which he didn't really specify what it is. The dependent variable is called job satisfaction. And you can see that it created basically a 2x2 plot, okay? So what we're gonna do is just delete everything here. But before we delete it, we can take a look. So it seems that for man, when the IV goes from 1, the dependent variable goes from 1 to 2, the dependent variable which is job satisfaction, increases. For women, when the independent variable goes from 1 to 2, the job satisfaction decreases. So you can think about what exactly it is, right? So the independent variable could be, I don't know, power, status, something like that. So, think about all these gender differences on that. But okay, so you can see at the bottom, it has this certain simple slope tests, right? So what it does is that you need to feed certain data into these cells so that it will do the test to the right-hand side. So you can see that the test results says that for the slope of man, the slope for man is 0.6. So B equals 0.6. T value is 13, and it's significant for men, and it's not significant for women, but the T value, the slope is in the negative direction. So what this does is basically tells us that the relationship between the IV and the DV is different for men and women, and it can tell you whether it's significant for men and for women. Okay, so at each level of gender. So what we can do is to clear the content of all these values in the yellow cells. We're just going to clear contents, so remove everything. And now you can see this table, this plot goes back to nothing. And there's some kind of a formula here hidden at the bottom, so don't change anything there, and don't change anything here because it's all formula filled. So don't change anything. If you double click it, you can see that these are calculated from the values to the left. So only fill the stuff into the yellow cells. Okay. So now what we're going to do is you need to find the values, which values to fill into these cells, right? So information that you would need to complete the simple slopes. The first is the regression coefficients of the regression coefficient table. The other is the covariate table. The covariate table, remember, we asked for it, right? We not only we asked for correlations, but we also asked for covariances. So the covariances is unstandardized value for correlations. You can think of it this way, right? So these are the covariances between these variables, okay? So remember, we have to pick one variable as the moderator. So in this case, let's say x3 is the moderator and x2 is the independent variable that we're interested in. Okay. Now, the next step is first you want to enter the values from the regression coefficients into the spreadsheet. Okay, so let's first enter the name of the independent variable because we want a name. So let's say that x2 is the name of the independent variable, name of the moderator is x3, dependent variable is x1. So that's done. The second is unstandardized regression coefficients. Again, this is just from the regression model that we saw earlier. So if you pull out your SPSS results, you can just enter these values into the table. So in this case, for our independent variable, which is x2, the b, now again, we're using centered scores, right? We're not going to use standardized, we're going to use centered results. So so the b for independent variable, you can see is 0.221. So we put in 0.221 there. But these are unstandardized regression coefficients, 0.221. Moderator is x3, centered, so it's 0.216. Put in there. And the interaction is just the regression coefficients of interaction is 0.326, right? And then we still need the intercept. In this case, is 16.595. Okay. The next step is we need the mean and standard deviation of the variables, which I have put it on. Okay, so you're basically copying, pasting from one spreadsheet to another. I'm sorry to make it so a little bit difficult because I try to copy and paste the whole spreadsheet, whole single slope spreadsheet into the data here, but it doesn't, for some reason it doesn't work. So we just have to remember these things by I don't know, using either text edit, so we can remember these values to make it simpler. I don't know, you can use write it down. I'm just going to use text edit to make a note for myself. So to make them easier to enter, x1, x2, x3. Okay, so the mean of the independent variable, which is x2, is 15.2. Put in 15.2. If you don't want to look, you can just follow me. The standard deviation of the independent variable, which means the standard deviation of, oh, actually, if it's centered, then it's 0. Sorry, the mean is 0. Standard deviation is 3.0414. The mean of moderator is 0. Standard deviation of moderator is 1.5253. Okay. So now we have the mean and standard deviation of variables. The next thing is the values of the variables at which to plot the slopes. Again, low and high value, in this case, we can just use one standard deviation, one standard deviation above the mean and one standard deviation under the mean. So the low value for the independent variable is just minus 3.0414, and just enter the minus 3.04, and high is plus 3.04. For the moderator, we also use plus and minus 1 standard deviation. You see, this is really just turning this entire regression equation using the specific values of the IVs and the moderator, so turn it into 4 predicted variables, right? So this is not okay. And now if you look at the data, it should give us the data already, but I don't know why it's not giving us the plot. Name dependent variable here. We can have optional alternative legend, but here we're just going to call it high, low, x1, x3, and x2. Not sure why this is not giving me the results. That's the problem. Like, yeah, it should be here. Should be somewhere hidden here, and these should be somewhere using the values on top, which I'm pretty sure I've entered. C57. C56. Where's C56? I think they're working. They should really give me that. I don't know why it's not updating. Is there an option to refresh? Select data. Yeah. Okay. For some reason, it's not giving me the update. Anyway, the key is that if you want to perform the single slope test, you need several things from the covariance table. So here's the covariance table to the left. Now you want to enter a few things. The first is the covariance of coefficient of independent variable. Now, to find that, okay, I'm not sure I've asked for that or not, so I'm going to do that again. So to get that covariance table, you would need statistics, covariance matrix. Yeah, I think that's it. I think that's the covariance table. Yeah. Options. Yeah, there's no other ways of getting the covariance. Oh. Create coefficient statistics, predict intervals. Yep, I'm pretty sure that's the covariance we were talking about. Variance of coefficient of IV, variance of coefficient of DV. Okay, guys, I'm not sure if the variance of the B is the same as the variance of these options of the variables themselves. So I'm just going to quickly check in SPSS if that's the case. And I've already closed my file. Have I? No. This is the Z value, but it's the same. Statistics, covariance matrix. If I select everything, residuals. So, yeah, I'm pretty sure that's the, oh, it included the covariance matrix. So the save, you should have included covariance matrix. And what would you find the covariance matrix at the end? Okay, it's the coefficient correlations at the end. It's not a covariance matrix at the beginning, but the coefficient correlations after the coefficients table, there's a coefficients correlations. Okay, what I'm going to do here is to quickly get that from the data we had before, so we can continue this one. Paste. C x2, x3, not x1, x3. Linear options. So we have save include covariance matrix. Okay. So the covariance matrix I'm talking about is at the towards the end, coefficient correlations. Okay. Actually, it is the ones that I've included earlier. Okay, right. So I was right to begin with. Anyway, variance of covariance of independent variable. Now, if you look at this table, you notice that the values, it's a symmetrical table and the covariance is the same for CX3. So it's a symmetrical table. So the variance is the values along the diagonal of this little table to the left, which I'm going to make it bigger so you can see it easier, right? So if you look at the covariance, the coefficient of independent variable, which is x2, is 0.020. Let's put in 0.020. The variance of a coefficient of interaction. So the interaction is x2, x3, and the variance is just at the diagonal of the covariance table is 0.005. Covariance of coefficients of independent variable and interaction. Independent variable is x2, interaction is x2, x3. Their covariance is 0.003. The sample size, what is our sample size? Sample size was, I can't remember, I think 20 or something, or 25. Sample size is 25. Number of controlled variables, because there's no other variables in our data, no analysis, so it's 0. But there we have it. We have all the information we needed. Still not giving me the plots. Where is my plot? I want my plot. Select data. And these are hidden, but they should have values. And that's what annoys me. People have these hidden cells that are doing the work, but it's not giving me the values. Not giving me the plots that I wanted. How about reset to match style? If I reset this, no. Oh, it probably has to do with the. Oh, it probably has to do with the values here on the vertical data. Let me see, automatic. If we set it automatic, well, that gives us the data. So X options. It is automatic. Oh, cross automatic. If we improve this, okay. If we change this to automatic bounds, finally it shows us the value. Okay, because it's out of bound. The dependent variable is just x1. Okay? So you can see that on the x-axis, you have x2, so you indicating from low x2 to high x2. So this is a very, very simple regression line with two data points. Okay? So you can see that when the x3 is high, that the relationship between x2 and x1 is positive. So x2 positively predicts x1 when on high x3, and negatively predicts x1 on low x3. Okay. So again, all we have here is just 4 predicted values and 4 cells. So basically, and these cells are defined using high and low values of independent variable and the moderators. High means 1 standard deviation above the mean, low means 1 standard deviation below the mean. And here it gives us the test of the slopes of x2 predicting x1 at different levels of x3. So you can see that at the low x3 level, the slope is negative, but if you look at the p-value closely, it's 0.08, which means when the x3 is low x3, this x2 does not significantly predict x1. In contrast, at the high level of x3, x2 seems to be predicting x1 positively, and it's significant at 0.05 level. Okay, so that's how you explore an interaction by creating this plot and by testing the simple slopes at 2 different levels of the moderator. So the idea, the term simple slope is similar to the term simple effect that we talked about during the analysis of variance. There are a couple of things here. First of all, Cohen has explicitly said that sometimes the low and high values does not even make sense. They don't even exist in the data file. So we are actually testing these hypothetical values instead of actual values here. Okay, so the so-called high and low groups, they don't really exist. It's just hypothetical values. It's predicted values. That's something to keep in mind. And the other thing is that the simple slope tests, actually I don't have any other thing to add. Okay, so if you're interested, because we still have some time, and I don't think I want to spend it on any other topics other than this one. So how about we look at the data that I just shared with you on the SPSS data that I just shared with you. So this data set is called Lecture 9, Religion IQ Violence Study 2. So it has, after I've deleted everything else, has these variables. If you double click on it, you can see that the variables are named country, which is the name of different countries, homicide rate within the country, religiousness. They have 3 different religiosity variables. I kept the one called Gallup, which I assume that has been using the Gallup method, whatever Gallup survey. And by the look of it, you can tell that it has been standardized because it seems that the maximum value is 1. So it goes from very small to large. So it goes from 0 to 1 with a lot of missing values. Also, you can see. NIQ. This is a very interesting data. This is a very interesting variable. So if you look at the label of NIQ, it actually says national IQ scores from Lin and Van Hanen 2012, supplemented from missing nations. So it's a calculated, it's some kind of a score, national IQ score from a previous study. Okay, that from these 2 researchers named Lin and Van Hanen. Now, that's something to keep in mind, and it will come back when we start to look at some of the criticisms of the data. All the other variables that's not really important include like GDP, Gini index, and population density, which we are not going to look at here. Again, what we'll be looking at is the 2 variables, religiousness and IQ, how it predicts homicide rate. So homicide rate is our dependent variable. Religiosity and national IQ scores will be our independent variable. And our each observation is a country, right? So we're talking about country level differences here. So each country is an observation. The first step, as we know, is to actually transform, that's what they did, is that they've transformed those 2 independent variables into Z-scores, okay? So we can do that by putting these 2 variables, religious Gallup and NIQ, and save standardized values as variables. You can click paste, but I'm just going to click OK. So now we have 2 variables that have been standardized to make it easier for us to work on. If you look at the distribution of these variables, you will notice that they're not normally distributed at all. Okay, we're going to come to that later, but let's just move on from here. And the next step is to create a interaction between the 2 variables, and we know that's done by compute variable. Let's just call it interaction, INT, IQ, religiousness, right? We know that it's a product term, so we just calculate a product of these 2 Z variables, click OK, and then we have the Z variable for interaction. So let's label it interaction IQ by religiosity. Now we have homicide rate as the dependent variable. So next step is to build a linear regression. So we put the homicide rate into dependent, and the Z scores and the interaction between the 2 Z scores into the independence. Now for statistics, we're going to look at descriptives, collinearity, part and partial correlation, confidence interval, covariance matrix, which we need. So continue. And we want to look at the residuals because we wanted to see if the residual is normally distributed. So histogram, normal probability plot, predicted value into x-axis, residual into y-axis, and we do continue. And options, everything else is just keep it as it is. You can paste. I'm going to click OK. Okay, so okay. Just waiting for my computer to come up. Now, you notice one of the problem is that the name of that the label for that variable is way too long. I'm going to rerun the analysis and remove the labels because that's just going to call the religiosity, and the other called IQ score because this is a huge long label which I'm really annoyed by. IQ. But that should be simple, right? If you haven't done that yet, make sure you change the label because sometimes they show you the results in terms of label, and then, yeah, as you see that it becomes quite cumbersome in the tables. Now you have the findings here, right? So we can look at the findings as this. The first thing is you can look at the correlations between these variables. We have 137 countries included in the analysis. The R square is 0.205, which is not bad at all. And the R is 0.45. And the entire regression model is significant, okay? So most importantly, you can see here, if you scroll it down, you can see that the interaction between IQ and the religiosity is significant at 0.035. And again, if that's not that significant, we wouldn't have to look at either the effect of religiosity or IQ. So it seems so far that it is doing what they're claiming. The result seems to be that there's interaction between the national level IQ and religiosity in terms of predicting homicide, and according to the authors, that is an indicator of violence. And we scroll it down, we can look at some of the residuals. So this is the standardized residual, and you can see that's how the residual compared, the PP plot compares the residual to normal to normal distribution. You can see that there's a clear violation of the normal distribution for residuals here, in that the residuals doesn't seem to be normally distributed. And this is the scatter plot that we plotted the regressions, the predicted value and standardized residual. You can see that there seems to be a pattern that when the predicted value increases, the standardized residual seems to increase, the variance increases towards the higher end of the predicted value, right? So there seems to be multiple violation of hypothesis here, of assumptions here. The other thing that we didn't do is to look at the normal the distribution of the independent variables, right? So we can do that by using the histogram, which in SPSS locates in graphs, legacy dialogues. I have no idea why they call it legacy dialogues. Don't ask me. And there's a histogram. And we can do histogram for the two independent variables. So we're going to just put in a Z religious Gallup there. And I'm just going to paste it because I wanted to do both histogram, right? So we're going to do two histograms. the other is ZIQ. So what we want to do here is to look at the distribution of the two independent variables. I'm just going to copy graph, histogram. Okay. And from what we can see is that they are not normally distributed at all. ZNIQ. Okay, so the name was wrong, ZNIQ. So in terms of religiosity, standardized scores is very strongly left skewed. Like, this is not normal distribution. And if you look at the IQ, there seems to be more normally distributed. At least it's more symmetrically distributed. Okay? So what is really required is to actually transform the score of religiosity using a log transformation. And so we can try to do that. And there's also some other ways of first reversing it and then do a log transformation. So first reverse the score, divided over one divided by one, no, one divided by the score, like reverse the score it. And then you can call it, instead of religiosity, you can call it atheism, like atheist scores, right? But in this case, let's try to transform the variable and see whether that solves the violation of normality issue. So you can call it Z religious relic transformed log. So I think there's arithmetic called log 10. So you usually use log 10 transformation, and you put the religious here. And that's going to create, I think, some problems when you have a very small value. Or let me just see. Let's see if I do OK. So now you have a log transformed religiosity score. We can look at the distribution of this one, right? Z relic log okay, so it's not ideal, but it's an improvement from before. And I think that if you, during the exchange, when you do the transformation, it's actually excluded a lot of variables, a lot of the scores, because it's impossible to, oh yeah, if it's under 0, then it cannot be transformed. Okay, so we have to scratch everything here and do a different, we need to transform the original score instead of the Z score before we do the log transform, before we standardize it. Right, so, okay, so this is the transformed score. Let's see that if that solves the problem. Okay, so that's after the transformation. Yeah, I'm not sure if that's solved the problem. And that's why for some researchers, they actually, for the person who criticized this study, they actually reversed the score first and add something onto it in order to do the transformation. But if we don't do the transformation like the author didn't, we can use the results and put them into the plot and see what the results say, right? Let me scroll up to the results that we found earlier and use this plot here to do what we, for the data that we just, the analysis we just did. So the moderator is called IQ. The independent independent variable is called religiosity. National IQ, dependent variable called violence, but it's more really a homicide rate. Put unstandardized coefficients in there. Minus 1.241. IQ minus 3.946. Interaction 1.939. Constant is 8.968. Since we have standardized the scores, mean and standard error is simple. It's simply 0 and 1. And to plot these, it's just put in -1 and 1 as the high and low value. So that part is simple. And the simple slope test, we need the covariance matrix in the covariance correlations table. So got to be careful about what values did you put in there. So the independent variable is the religiosity, 1.34. Interaction is 0.825. Covariance is covariance between the independent variable and interaction is minus 0.641. Sample size in this case is 136, and we don't have any other variables there. So we have suicide rate at x, y-axis, and religiosity. And you can see that this is what they have claimed. For countries with higher IQ, their suicide rate is lower, but also religiosity does not predict suicide rate. No, homicide rate. What? Homicide rate. And the slope is not significant, as you can see here, the slope test. And for low IQ countries, their homicide rate is higher, and religiosity seems to be lower, the negatively predict the homicide rate. And the slope is marginally significant, which means between 0.05 and 0.1. And they have run the analysis with different kinds of IQ indexes, different types of religiosity indexes. And they claimed that they found the same pattern across different analyses. And using this evidence, they're making the argument that the religiosity program, the education about religiosity, or like a religion education program, might have better effect in countries with low IQ. Now, this has, again, become a hugely controversial findings, hugely controversial, mainly because of a few things. I will include a criticism paper in the shared folder, but most importantly, first of all, the IQ scores, remember that's from the two professors called Lin and Van Hanen. And if you look into the Professor Lin, you'll find out he is an extreme, he's a white supremacist believer, he's extreme right wing. And so in his study, he found that this IQ score is negatively correlated with skin color, and this national IQ score. And they're claiming that this is a evidence that suggests that their IQ score is valid, but that's not the case. That's because skin color has nothing to do with IQ scores. At least there's been controversies about that as well. But that just sounds like they're using the IQ scores to the so-called IQ scores that is merely a reflection of racist beliefs. And so that if the IQ score they're using is problematic, then the entire study the conclusion become problematic. The second thing is that additional analysis of the data, including other variables, such as slavery history of slavery, and other variables I can't remember, but I think history of slavery is, once you've entered that as a predictor into this particular prediction model, then the IQ and religiosity becomes insignificant, become non-significant predictors, which might suggest that in order to predict violence, slavery history is a much stronger predictor of violence than these other variables. So that's one criticism that I've read, particularly against this paper. Of course, the same criticism has pointed out these issues about the distribution of independent variables. So if you're interested, I can include that criticism paper, which I think is a very strong criticism, into this into the shared folder, and you can work on this data set when you have your own time. I can even include the full data set in there, so you can look at it and see. And they have shared the data set, their syntax file, and how the variables are coded. So that's all publicly available and shared. Okay. So that's it for this lecture. Before we wrap it up, I just want to quickly mention one thing, is that we haven't really covered the situation where you use multiple regression using categorical variables as the independent variables, which would require is you have to turn categories into binary variables called dummy variables using different kind of codings. So for example, if you have a categorical variable with 3 levels, then you would need at least 2 dummy variables to represent the 3 categories of this categorical variable. So that's not covered in this module, in this class. But if you're interested, you can take a look at Bob Gardner's slides about this, how it's done. It's not that complicated, but it does require paying attention to how the categories are coded using 1, 0 or 1 minus 1 or other kind of coding methods would influence your results. So that's it for today. And next lecture will be our final lecture. We will not be looking at the data analysis, but we're going back to some issues about research design, about a measurement related issues that we never had the chance to address, and a review of what we have learned throughout this module. And yep, that's it. I'm going